Okay, in this video we'll look at rational functions. So a rational function is just a fraction of polynomials. So if we have a polynomial p and a different polynomial q, then this is a rational function. And now the terminology is because if a rational number is something like an integer divided by a different integer. Okay, so some of the properties that these things have. One, we always have to worry about the domains, and that's because we have some function in the denominator. Okay, so we have to worry that is g of x ever equal to 0. Now, graphically, these things oftentimes have asymptotes. Okay, so what one of those will look like, we'll just kind of make a quick sketch over here. So let's say here are our coordinate axes, and our function looks something like this. Then this vertical line here is an asymptote, and basically all that means is that the function's graph is approaching that vertical line, but it never actually reaches it. So there are several kinds of asymptotes that you can have. You can have vertical, as in the example we drew here. There's also horizontal. And then the last kind, which is a little unusual, are called either slant or oblique asymptotes. And those are a little complicated, so we'll talk about them in class, but the vertical and the horizontal ones are relatively straightforward. So let me draw in the horizontal one here. My graph isn't the best here, so let's pretend that's a horizontal line. So basically the red curve is getting closer and closer to the blue curve without actually ever crossing it, and my picture notwithstanding. Okay, so that's basically the idea of what these asymptotes look like. So the horizontal asymptotes are basically just asking what's happening way over here and what's happening way over there. Okay, so horizontal, what happens when you have really, really big or really, really small x's plugged into the function? Does it look like the function is sort of leveling off? And then the vertical is whenever your function values, oops, not 8, infinity, whenever your function values start blowing up to plus or perhaps minus infinity. So on our picture here, that would be the blue line, because the y values are just going up without bound as the x coordinate gets close to whatever this is here. All right, so in the next slide we'll look at a quick example. Okay, so the first example we'll look at is we'll just let f of x equal 3x over x minus 1. Okay, so this is a pretty simple rational function. Both the numerator and the denominator are linear, and so we're going to ask sort of a couple questions to try and figure out where should the asymptotes of this thing be. Okay, so the first thing is really just to fill out a giant table. So if I plug in a bunch of x's into this function, let's just sort of intuitively examine the behavior. Now we might look at this and say, okay, well we clearly have a problem when x equals 1. We've already done that stuff before. but what's the behavior when x gets really, really close to 1? So let's just kind of write some numbers down. So we'll plug in some x's into the function, and we're going to get out some f of x's, and let's just see what we can get here. So let's first pick some x's that get really close to 1, and so we'll do something like, say, 0.5, 0.9, 0.99, and just to really kind of drive the point home, we'll do 0.999. Okay, so if I want to plug these into the function, just plug them in for x and do some quick calculator action. That's okay here because we're just trying to sort of illustrate roughly what's going on. Later we'll learn more exact processes for what we're doing here. So so I just cheated and I've pre-computed all of these, and so f of x turns out to be -3, and then this one is -27, and then -297, and then the last one is -2,997. Okay, so basically what's happening is as we approach 1, our numbers are getting ridiculously negative, and you know, by a factor of 10 sort of at each extra digit that we go down. So what we should guess here is that the behavior is that as x gets close to 1 from the left, f of x is going to -infinity. Okay, so this should make us guess that something is going on at 1. Okay, now we'll do the same thing for the other side of 1. So here I approached 1 from the left by getting just taking numbers that were just a little bit smaller than it, but we could also do this from the right, and so sort of construct the same little table here. So here we'll put some x's, and we'll have some f of x's, and the numbers that I'll do here, kind of the same pattern. We'll start with, say, 1.5, then do 1.1, 1.01, 1.001, and see what we get. So again, I just pre-computed these just for the sake of time, and I got 9, 33, 303, and 3003. Okay, so sort of the same behavior as what we saw in the last one, except that instead of the numbers getting more and more negative, these guys are getting more and more positive. So as x approaches 1 from the right, it looks like the f of x's are going to +infinity. Okay, so there's definitely something going on there at 1. Okay, and then lastly, let's do sort of some long-term behavior for this function. So I'll make one more chart here, and we'll put my x's here and my f of x's here. All right, so for these, I want to sort of think what's going to happen as the x-coordinate gets really, really, really big. So we'll just do sort of 4 of them here. We'll do 5, 10, 100, and then 1,000. Now, you would probably never actually put all of these on a single graph, and that's fine. We just sort of want to imagine if we did make a graph that goes all the way out there to 1,000, what, roughly speaking, is going to be the long-term behavior of the function's graph. Okay, and so again, I pre-computed these, and we got 3.75, 3.3333, and this one I had to round to the 4th decimal place. That's okay. 3.0303, and then lastly 3.003. Okay, so looking at the evolution of these numbers, basically it's looking like they approach 3. Okay, so as x gets really big, it looks like the f of x values are settling down on 3.0 on the money. Okay. All right, so from this we should guess that we have probably a horizontal asymptote of y equals 3. Okay, so y3 because of this guy right here. And then we should also suspect that we have a vertical asymptote of x equals, well, what's the x coordinate where some stuff is kind of going on? We said it looked like x equals 1 was where the issue was going to be. Now, looking at the vertical asymptote, it's perhaps not surprising because the domain here is everything but 1. We already knew that. And then graphically, we're just saying, okay, what's the behavior look like close to 1? The function, of course, is not even defined at 1, but sort of near 1, what does the behavior look like? Okay, and then just a quick sketch of the graph. It would look something kind of like, so here's coordinate axes, and then we said that our vertical asymptote here is going to be when x equals 1, and our horizontal asymptote is up here at 3, and so I'll just kind of eyeball this, and we basically are going to get something that looks like this. That way, and then this way, roughly. Okay, so why should the graph, roughly speaking, look like that? Well, on this side of the red line, the x's are slightly bigger than 1, and the behavior should be that we go up to infinity. That was what we saw in this section here, the middle batch of numbers. As we approached one from the left, so that would be this batch, the y values are nosediving down towards minus infinity, and then for very, very large values of x, we said it should sort of settle down on 3, so it should kind of go towards the blue line. Now, the one thing that we didn't really compute here, and so I'll leave this sort of as an exercise for you, is compute the same stuff here, but do it for -5, -10, -100, -1000, and that'll tell you that what the behavior is over in this vicinity of the graph. And not surprisingly, you're going to get 3. The only difference is that the numbers will be just slightly smaller than 3. So you'll be seeing stuff like 2.9, 2.97, something like that. But the numbers are going to be getting closer and closer to 3. Okay, so that's basically the idea here. We'll talk in a little bit more detail in class as to how you can really carefully figure out the horizontal asymptotes without doing this sort of numerical game, and then also what to do if there's a thing called a slant asymptote, which is a little strange. Anyway, okay, well, we'll see you in class.